Hello, AD, and as soon as you join me, go ahead and let me know you're here. And if you're watching this video, you need to write to me and let me know that you've watched it and taken notes on it afterwards. Thank you. So it's not quite time, but as soon as people come in, I will ask them to let me know they're here. So just say hi, and then I know who I've got here, and I'll take roll as we do this and give you guys some points for participating. And we'll learn a little chemistry here in a few minutes. So, got two people already. Okay, who are you? Good morning. And there's three. Super. So, I've got Tara. I've got Life. Great. Tara, you're set. Life is here. Good. I've got Ava Elena, and I don't know who that is. Do I have an Ava Elena? You'll have to tell me who you are. Okay, Albert is here. And Solomon's here. So Ava Aliana, tell me who are you if you're not in my class, and then let me know. Again, this is for 8D physics. Thanks, Solomon. Okay, alles klar, very good. So we'll wait a couple more minutes for others to join us, but yeah, how you guys doing? And did any of you start the little simulation periodic table I sent you? And if you did, how did it go? Was it okay? I thought it was kind of cool. Tells you a lot of neat stuff. Solomon's done it, and hopefully it went okay. Let's see if anybody else has questions or comments on it. All right, Tara's done it as well. Very good. And Albert said it was good and kind of fun. Yeah, good. I mean, it's a periodic table, but still, there were some kind of cool things you can learn about the elements by doing it. Shvitri is here. Hi, good morning, Shvitri. That is cool. Good. Let's see if some others join us here. I hope. And we'll give another couple minutes to allow people to join us, and then we will start up for the day, finish up with families of the periodic table, and review some trends, and talk about weird hydrogen. Okay, any questions while we start up? Hope you're all doing okay at home. Is everybody in your pajamas still? I don't want to know. Just kidding. Let's see. There's another person. Sign in. Let me know who's here. Oh, Sophie's here. Morning, Sophie. And if you've got a little baby periodic table or one from your planner, please get it. So find a periodic table. That would be swell. Amalia's here. Dynamite. Very good. So find your periodic table if you're joining us. That would be terrific. And we'll start up in just a minute. But I've got I don't know everybody, but I've got a bunch of you, and that's cool. Okay, I've also got some new markers, so I hope you can see better today. I'm going to use those and a new eraser, huh? Fancy? So we'll leave my attendance taking here. And why is the video called a test? Because it was the first thing I put down for a title, Solomon, and I usually change it. So it will get changed to 8D Chemistry 3420 when I'm done, but it comes up as test video. Don't worry about it. I'll have to deal with it. Okay, so let's see where we left off last time. We left off with a couple of families yet to talk about. Let's talk about this family, okay? The nitrogen family. It's the top member is nitrogen. I don't have another fancy name for it, so we'll just call it that. So can you see that? Yes, you can. So nitrogen family. You tell me. So all those suckers tend to want to gain how many electrons if you're in the nitrogen family to get a full shell, right? Remember the game, right? Everybody wants a full shell. So if you're in family this guy, how many would the members have to get a full shell? And if you're just joining us, say hi so I know you're here. How many electrons does the N family take or gain? Any guesses? Nitrogen, how many electrons do they tend to get to fill their shell? They're right here. So tend to gain electrons to fill, let's call it the energy level. That's the more modern term for it. Good, some of you got it, and it is, Alicia's here. That is cool. 3. Welcome, Alicia. Good to have you here. Okay. Yeah. So to fill the energy level. In other words, and maybe this is the question I should have asked. In other words, nitrogen and the other members there got how many valence or outer electrons? How many are in that outer shell? Do we have to take notes? Well, yeah. So whatever I write here, Albert, please take notes on, because it is a good way of learning is to write some stuff down. Okay, I'll try and write large enough and get rid of the shine now and then so you can see what I wrote. So far we got nitrogen family tends to gain 3 electrons to fill the energy level, or we could say we got valence electrons in that family. So how many are in the outer area there? 4. I think 1 more, isn't it? If they need 3, so we got 8 to fill the shell, so we must have 5. You got it. That is right. Yeah. Right up. Good. Okay. 1, 2, 3, 4, 5, 6, 7, 8, and 8 of you. Okay, good. We'll continue. Looks like I got everybody here that's going to be here. With the nitrogen family, the reactivity varies. In other words, some of the members are more reactive than others. That's all I want to say about that family. All right, let's go on and do the carbon family because they're a little more interesting. Okay, let me ask it the other way. How many valence electrons does the carbon family have? Okay, so it's carbon number 6 and the members that are below that. The carbon group, I should call it. That's a fancy name. So how many in that group? So have valence electrons. Can you see that? Yes, you can. And they've got 5. No. That was from the last answer. I hope. Yeah. Carbon has got, well, it's got 6 electrons, right? Remember how we did this, right? So remember our shape, 2, 8, 8. So it's got 6 electrons. So in the first energy level, 2. 2 from 6 is 4. So we got 4 left for the outer one. So it's got 4 valence electrons. Therefore, here's the interesting question. Good, now we're coming online. Yeah, 4, Tara's got it, Amalia, and so on. And somebody's joined us. Let me know who you are. To get a full energy level, what is carbon gonna do? Or the other members in the family can do what with electrons to get 8 in the outer energy level? What could they do? Those group members. Yeah, thanks, Sophie. So they can gain 4 electrons. Or what? Or what? They could gain 4 electrons, or how could they also end up with a full energy level? Lose 4 electrons. Thank you, Amalia. So in other words, this guy can go both ways, carbon and silicon and these other members. That's why a lot of them are metalloids, okay? Many of these are metalloids, including carbon, silicon, and germanium. Are semiconductors. You might have heard of that industry, the semiconductor industry. Ute. Last group is the boron group. Let me not get sloppy. Maybe I should say the others are groups as well. That's the fancy correct term on the periodic table. I like to think of them as families, but they're actually called groups. Why can't they lose more than 4 electrons? They can, Solomon. They can lose all their electrons if you put enough energy in and whack them away, but it's difficult. If you got 8 electrons, I can take all 8, but it sure takes a lot of energy to. Yeah, it's more common, right, Sophie, that you pull off electrons until you get down to a full energy level, or you add electrons until you get to a full energy level. Okay, the B group, this is not like B as in AB, it's boron, okay? So it's these puppies right here, and these guys got valence electrons. Let's hear some new people. How about Alicia? How many valence electrons does this family have? And what they can do to get a full shell. But Alicia, tell me how many valence electrons these suckers have. Who else haven't I talked to yet? Alicia is correct. They got 3. So let's go to Tara. Tara, what can they do to get a full energy level? Could be 2 answers. Can or what was the N again? The N was nitrogen, Alicia, nitrogen. Good. So Tara writes they can gain 5 electrons or lose, not 5, careful. Yeah, exactly, lose 3. And it's kind of a weird family. Frankly, boron is a nonmetal. The rest are metals. It seems like about 1,000,000 years since I did that lab with you, but I mean, we did notice that non-metals had certain qualities, metals had other qualities. And so below boron is aluminum, that's like a classic metal, gallium and so on. These are all metals, so they got pretty classic um, metal properties. In spite of the fact that aluminum's right on the line, it's not really a metalloid. I don't buy that. It's mainly a metal. I got chunks of it here. We make cans out of it, right? Okay, but boron is a nonmetal, the top member, so it's kind of a mixed family that way. Okay, that's kind of it, except for one important member on the periodic table. First off, let me look here and see if you guys have written those, and if you got any questions about those notes. If not, I'm going to use my handy dandy new eraser, and let's see. What classifies things as families? Yeah, let's call them groups. So the deal is, Solomon, the groups are these guys. In other words, we're going to skip the metals in the middle, but the groups we've learned already are the ones that act like a big family. So I got the AM, that was the what? Alkali metals, right? I got the alkali metals group, and they have similar properties. That's why I call them a family, okay? And the alkaline earths, similar properties. The boron group, carbon, nitrogen, oxygen, and halogen group, and noble gases groups. So really what we're talking about, groups have similar properties. Maybe we knew this already, I don't know. But groups have similar properties because they have similar electron structures. I don't know if we said that, or let's write that over here. Groups, similar properties, due to similar, well, let's put it this way. How about the same number of valence electrons? Due to same number of valence electrons. Okay, and I know a couple of you are still writing, so I'll see if there's any other. Yeah, so it's classification, Solomon, about the way they behave. And scientists really think they behave because, hey, like these guys all have a full energy level. Or, hey, these guys all have one valence electron, the alkaline metals, for example. So they behave in a really similar way. Huge. Okay, I'm going to start to erase. Let me tip it so you can see areas that might have been under the shine. If you're still writing. There we go. Okay. If not, you'll have to go and check out the video and get the board. But I gotta keep going here. Only got 45 minutes with you. It's time to talk about, is boron the only nonmetal in that group? Yes, Sophie. It's time to talk about my favorite schizophrenic element on the periodic table, and it's sort of problematic. Ooh, somebody joined us. Let me know who you are. Let's talk about weird hydrogen. Okay, check out hydrogen on the periodic table, okay? It's the first one, right? It's up in this corner. Okay. Life, I haven't talked to you that life, hydrogen got how many valence electrons? Hydrogen. So life, how many valence electrons does hydrogen have? Waiting for a response, so I'll just take one from, who else is here? How about from Albert? So how many valence electrons does hydrogen have? One. Thank you, Albert. Okay, so now the big question is to have a full or completely empty energy level, hydrogen could do what or what? To have a full energy level or completely empty energy level, hydrogen could do what or what? Yeah, Tara, good. It can add or lose one electron. And Svetria says the same. Good job, ladies. Okay, so, and hydrogen also got a problem, okay? Hydrogen, here's hydrogen. There's the proton, right? And there's one electron, right? Albert says we got one electron. So the problem is poor hydrogen with one proton, this electron, it often is lost to other elements where the electron is like, okay, I feel a pull here, but man, that other one has a lot more protons. Bye bye. Okay, bye bye. So hydrogen often loses its only electron and then has a charge. We say it's hydrogen plus because it loses an electron, so it has one less negative. We'll talk about that more in a bit. But for now, I want to talk to you about why it's so weird. Okay, hydrogen. I can't write on the board with that. Hydrogen. It's first off, it's it comes as H2. In other words, if I have some hydrogen, they come in twos. And so it's a molecule. What's that called when they come in twos? A molecule. Give you a hint, starts with a D. And compound, no. A compound tar would have two different elements, so it's not going to be a compound. Dihydrogen, yine, it's a Brinkelhoff, yes, Sophie, but what does that mean? It's a di, which means two, atomic element. Do we not have that word diatomic? Two atoms? And that's what the Brinkelhoffs are. Yeah, diatomic. Yeah, okay, there you go. So it's diatomic, okay? That's what that means. All the Brinkelhoffs are diatomic. So important word to know. What other family what other family has a lot of diatomic members? Give me another family that has a lot of diatomic members. And yes, Sophie, it more likely loses one than gains one. You're right. What other family has diatomic members? Think of all the families. Oh, sorry, groups. Shvitria's got it. Well done, Shvitria. The halogens, yeah. F2, Cl2, Br2, I2 when they are elements. Dynamite. Okay, so it's that like a halogen. Okay. But it's in a family that tends to lose, easily loses its electron like a Okay, which side of the park? Which side of the park? Huh? Which side of the periodic table tends to lose electrons? That side or this side? And that means if it's on this side, it's acting like a what if it loses an electron? What is today's title, Sophie? Let's call today rest of periodic table. Thanks, Sophie. Keep me honest here. The rest of the periodic table. Okay, we got all the groups done, and now we're down to weird hydrogen. Okay, so it's acting like a, if it loses an electron, acts like a, starts with M, rhymes with ethyl. Okay, a metal. However, what phase is hydrogen at room temperature? If I had some hydrogen, some H2 in my hand, then what phase would that stuff be? Solid, liquid, gas. Those are the phases, right? Hydrogen at room temperature is what phase? It's a gas, right, Smitria? And right, Tara? So it's a gas at room temperature. Yeah, good. Everybody's got it. Well done. Okay. Here's something really weird. I can make hydrogen into a solid. I got to cool it down to like really, really cold. You remember the Kelvin scale? Like the coldest possible thing you learned last year, okay? 0 Kelvin is absolute zero, or it's negative 273 degrees Celsius. You can't get any colder. So if I can cool it down that far, or even close to that, maybe 270, negative 270 degrees Celsius, hydrogen would be a beautiful silvery metal. So when at negative 270 degrees C, it's shiny and silvery like a metal. Hydrogen is schizophrenic. In other words, it doesn't seem to know its identity, right? It's pulled. Oh, I'm diatomic like a halogen. Oh, but if I'm cold, I feel like a metal. Oh, but I'm a gas. I feel like a halogen. Oh, you see what I'm saying? It's got a problem. So it's got a bit of a split personality. Some folks, ready for this? On some periodic tables, you may see this. So if you see it, don't freak out. They don't put hydrogen here, they put it over here. So some folks think of hydrogen as being almost having traits of the halogen family. So hydrogen is weird, okay? So it's like a halogen, but it's also like a metal. So it has metal and non-metal properties. Mostly, okay, so H has metal, non-metal props, but at room temperature, it's mostly a non-metal. And hydrogen is found in all what? Now I'm going to continue here, okay? Hydrogen is found in all what? Water, yes. Good. Okay, good. Yeah, that's not what I'm after, but I'm after something else. It is found in water. Two of them are in every water, but they're found in all acids, like citric acid, right? That's in fruit. Vinegar is an acid. Anything that tastes sour. You're going to study acids a lot next year. Okay, so hydrogen is in all acids as H plus. And here's the really weird thing about it. It's as H plus, and H plus, H plus is just a what? What is H plus? It's simply a what? Starts with P. Rhymes with oton. H with a full energy level? Actually, not. This guy has lost it, so it's lost its only electron, H plus. There you all got it. So it's nothing but a proton. And yeah, what did I just want to say? Most hydrogens don't have any neutrons. So really, I just got this little proton, and that's an H plus because someone else has pulled off its electron. That's just the way it is. Okay. Ute. All right. That's enough of weird hydrogen. So you get the idea. It's a non-metal, but it acts like a metal sometimes, and it's really undecided. Partly a halogen, partly a alkali metal, but we mostly think of it as a non-metal. And next year it'll be bonding like a non-metal. That's not a dumb question at all, Shvitra. Hydrogen does have a nucleus, and the nucleus is the one proton. So essentially, Shvitra, you can think of as hydrogen, if it's H plus, it's got only a nucleus and nothing else. So think of it being like a soccer ball in the middle of Olympic Stadium and nothing around it. No electrons, nothing, just the nucleus. And it's a tiny nucleus, it's a proton. It's a good question. Okay, let's go ahead and go on a little bit. And in our time remaining, review these trends, okay? Okay, so trend review or trends review. I want to review because, frankly, some of you missed this on the homework. So on a base periodic table, well, okay. Turns out we got three trends. It's atomic radius, and that's really the important one. So turns out if I go across the periodic table this way, and some of you kind of got that, I add more protons and more electrons. But the deal is the electrons that I add are not in a different energy level. So really what's important is that I go this way, I got more and more protons. So what happens is, whoa, there's my electron. So let's say I got one proton, now I got two, now I got three, and I start to pull this electron. Well, even if I got more electrons, the more protons I got, the more these things are pulled closer to the nucleus. So that's the scoop. As I get more protons, the atomic radius gets smaller. So for this way, I go from here to here, and that's decreasing atomic radius. These guys tend to be bigger, these guys tend to be smaller as I get over on that right side of the periodic table. I know you had this on the periodic trend homework, but it's important, so I want to review it, especially in the next couple, because you're having more in the next years. The next one is, so that's the direction of increase or decreasing atomic radius. Let's do another little puppy here. And this time I want to talk about ionization energy. Okay, ionization energy energy was the energy to take a from an atom. All right, everybody should know this from the homework. Everybody should know this, okay? So type it in. So what was ionization energy? It's energy to take a from an atom. An electron. Svidria, you are red hot today. There we go. Or you got a fast microprocessor, so you're beating everybody else. Tara's got it too, and Albert. Okay, and others. Okay, so let's think about this. Well, we already know hydrogen loses its electron pretty easily. Which side of the table, metals or nonmetals, tend to lose their electrons easier anyway? Who loses electrons more, metals or nonmetals? Who loses electrons more, metals or nonmetals? Need another guess. Who loses electrons more easily? Kind of hard to keep track of all this, isn't it? Yeah, Albert's got it. So it's the metals. So this side, they tend to lose electrons as they get closer and closer to this group. That's the noble gases out here. They tend to lose less and less electrons. They do not want to lose them because it's a way to get a full shell. So what happens is this is the direction of, and by the way, the abbreviation here is IE, ionization energy. It's what everybody uses. I might as well let you know. So this direction here, going up towards helium, for example, is increasing ionization energy. Hydrogen, easy to take. Cesium, really easy to take. We'll talk about why that is in a sec. Helium, really difficult to take an electron. Okay, let's talk about cesium for a second. Okay, cesium. Everybody kind of find it there. It's number 55, CS. It's got 1, 2, 3, 4, 5, 6 energy levels. So here's the nucleus, and this thing's got boom, 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 boom levels of electrons. So the question I got here is that the protons in the middle of cesium, what's the problem with them holding on to these electrons way out here in the 6th shell? What happens to my distance? So there's the nucleus, right, of cesium, the first energy level, second, third, fourth, fifth, sixth, way out here. What's the problem? If I have a big distance with these little electrons, what's the nucleus not going to be able to do very well? So again, electrons, energy level 1, 2, 3, 4, 5, 6. That little nucleus is not going to be able to the force. It's actually an electrical force, but yes, the electrical force decreases exponentially. So this is something, it gets weaker. Yeah. Okay. So the force gets weaker. So in other words, yeah, the further away this is, and we learned this when we had physics, right? The further the distance, the weaker the force. So what that means is the electrons out here can be pulled off pretty easily. It's sort of like saying, hey man, I got an apple tree and the apple's way out there. I can't really hold on to them very well. So they're pulled off easily. So easiest to pull off would be like francium, named for where it was discovered. Hardest, helium up here. Let's do the third trend before we run out of time. Third trend is electronegativity. Baby periodic table. And electronegativity, let's write it over here. It's the ability to attract, guys, be nice now. It's the ability to attract electrons. I call it electron hoggability. Hoggability. And the biggest hog on the chart, fluorine. So the noble gases are kind of out of this one, but fluorine, man, it is a big hog. Fluorine wants electrons like crazy. Okay, so whereas francium way down here, oh man, the furthest ones are so way out. I don't really want that many electrons. You can take the one I got, the extra one, okay? So this is the direction of increasing electronegativity. In 10th grade, 2 years from now, you're going to need to know that fluorine really wants electrons, and it's important that it does. Another two that really like electrons are N, O, and F, okay? So let's write here under electrons. So the most electronegative, the biggest hogs on the planet, electronegative, are N, O, and F. Okay, Ethan is there. Okay, Ethan, you can see the other boards on the live stream. I'll send that. You'll be able to see that if you want to repeat it later and see what's going on. They are far away. Yeah, they are indeed far away. So, okay, so N, O, and F, big hogs, and yeah, you're going to learn more about that in 10th grade. I think I'll pause there for a second. We got just a couple minutes left. Let me tell you what's going to go on next time, because I think you're going to like it. It'll be worth showing up, and I hope more of you show up. So next time, bring your periodic table, and we're going to look at the numbers. And it turns out the numbers tell a really interesting story. It's not boring math, it's cool math, and it will make your eyes pop out next time, okay? Specifically, we're going to look at the numbers here of the noble gas family. But the last couple minutes, let's just play a family quiz, all right? I'm thinking of a family, and this family, can you tilt the board? Yeah, I can, Sophie. How's that? I'm thinking of a family. This family tends to lose 2 electrons? What family am I thinking of? Oops, sorry, group. So this group loses 2 electrons typically. What group am I talking about? What group loses 2 electrons? You can check your notes from last time, because that's when we talked about this. And Solomon's got it. Let's see if a couple others are there as well. Sometimes your answers come in slow because of who knows what in the world of computers. So yeah, it's the alkaline earth family, okay? So these puppies, Svitri's got it too, alkaline earth family, right? Okay, what family tends to gain 2 electrons? What family, what group? What group tends to gain 2 electrons? What periodic table group gains 2 electrons? And it is the oxygen. Yay, Sphitria. Oxygen group is right. Good. Our time is over. We're going to continue with our math mystery next time. And if you haven't finished up the assignment, please do so. Thank you, everybody, for participating. We'll see you next week. Be well. Stay healthy. Bye-bye.